All right, so because we've defined probability distributions on our data, that, that implicitly defines the joint likelihood of the data. So let's look more specifically at what that is. So we've defined a joint likelihood on all of the labels given all of the covariates and the regression coefficient vector W. The independence assumption allows us to say that this joint likelihood is equal to the product of these individual likelihoods of each observation pair. And we're going to use the notation sigma IW just for a few slides. So the way that we can write this probability, we know that it's a discrete probability on two events. We're going to write it this way, where we take the probability of the label being +1, raise that to an indicator of the label being +1, times the probability of the label being -1 raised to an indicator of that event. So this simply picks out the correct event. For the true value, we're going to have the indicator equal 1. For the false value, for the wrong value, it would equal 0. In which case, for example, if the label is equal to +1, then this picks out sigma I, whereas this term is raised to the power 0, so it equals 1. So this picks out the correct value, sigma or 1 minus sigma, for each observation. And now notice that this distribution on observations is data specific. So even though we can write it using one simple notation, these probabilities are actually changing for every single observation that we have. And they're parameterized by the covariates x as much as they are by the coefficient vector W. So we're going to discuss an algorithm for maximizing this in W. Notice that when we do learn the vector W, prediction for new data is fairly straightforward. If we wanted to predict the most likely label, then we would simply take x, a new x, and evaluate the dot product with the learned W and declare the class to be +1 if it's positive, -1 if it's negative. But we actually also get a confidence of our prediction in a sense. So we get this probability of the label. So some labels that we're more confident in, we'll be able to say we're very confident it's +1, whereas the labels, whereas the data that fall close to the separating hyperplane will be less confident. So we could say we're, say, 60% confident or something like that. Okay, so there's one more notation change to be made. Again, these sorts of changes are done purely for convenience so that there's less to write. But they make life a lot easier. So let's use this this fact here. Let's build in the label into the sigmoid function itself in order to pick out the correct one for us. So instead of originally having this, which is again, remember that this is the probability for the ith observation of the corresponding label being equal to +1. So that's the sigmoid function of the probability of a +1. 1 minus that is the probability of a -1. Instead of writing it this way, what I'm going to do is I'm going to feed as the argument the label times the dot product. And if you want to see why that makes sense, notice that if y is equal to +1, then the right-hand side is equal to this times 1, because this is equal to 0 in that case, so this is equal to 1. And again, y is +1, and so this, of course, is equal to that. And then when y is equal to -1, notice that this right-hand side is equal to this term here. And then you can quickly verify that if we actually replace yi with a -1 here, that actually this term is in fact equal to this term. So therefore, using this simpler notation, we can write the joint likelihood as equal to the product of these sigmoid functions, where we also multiply the argument of the sigmoid function by the label +1 or -1. So that's why for logistic regression, it's often a lot easier to assume that it's +1 -1, whereas for the Bayes classifier we said +1 or 0 because subscript with a 1 or a 0 looks nicer than subscript with a +1 or a -1. These are just arbitrary choices that are made to make things easier to read and easier to write. Okay, so we've defined the model. We've defined the likelihood term of the data given the parameters of the model. Now let's look at one simple, straightforward way to learn this model. So if we've only got the likelihood to work with, naturally what we would want to do is maximize that likelihood with respect to the model parameters. So we end up with this sort of a situation where the maximum likelihood solution for the vector w is equal to the vector that maximizes the log of the likelihood of y given x and w. From the previous notation, that's equal to this. Let's define this objective function as L. So L is equal to the log of the likelihood of y given x and w. Again, as with the perceptron, we can't take the derivative of this thing with respect to w and set it to 0 and actually solve for w. There's no analytic solution for finding the solution to this. So we're going to need some sort of an algorithm, an iterative algorithm for learning w. So we'll look at the first thing to consider, and what we'll talk about in this lecture is gradient descent. So we want to iteratively refine the vector w. At each iteration we set the update to it, to the vector w, equal to the old value, plus some small step size that's positive, times the gradient of the objective function evaluated at the current value. And in this case, you can verify that given our definition of the sigmoid function, when we take the log of it and sum over all of the data instances and take the gradient, we end up with a function that looks like this. Notice that this term is some number between 0 and 1. Y is just a sign, basically. It's plus or minus 1. So this is simply flipping the direction of x, which is a vector. So this term is a vector. We're summing each of these data-specific vectors to get the gradient. This is the direction in which to move to increase the objective function, and so we take a certain step in that direction to update our vector w.